Welcome to Geometrical Optics. These lectures will probably be broken into several parts, but first we're going to develop what happens when an electromagnetic wave reflects or passes from off of a surface or passes from one medium into another. Simplest case, of course, is reflection. So when you have an incident ray like the one here that hits a surface and then reflects, it turns out if you're going to trace the path of this ray, or if you're going to trace the path in essence of a photon, although it's not really the same photon after the surface, but if you're going to trace this path, the incident angle and the reflected angle are the same, and the angle here is the angle perpendicular to the surface, right? And we use the angle perpendicular to the surface because the surface might not be flat, the surface might not be symmetric around this point, in which case the angle with the surface isn't as well defined as the angle perpendicular to the surface, right? So basically what I'm saying is this would hold true even if these angles weren't, because of surface curvature, weren't the same. Now, how do we get to that result, that the incident angle is equal to the reflected angle? Well, consider an incident wave that's coming in, right? And here are all the wave fronts. Once it's reflected, one of the things that we know is that the velocity of this point, right? Velocity of this point right here, or that point right there. The velocity of this point is traveling this direction at v equals to c sine theta I. And that's for the incident wave, right? That's the component of velocity of the wave in this direction. We also know, if we looked at the reflective wave, that the same thing is true. Right? On the reflected wave front, that velocity of that point that's in contact with the surface is traveling that direction at v equals c sine theta r. Well, these velocities have to be the same because those points travel along the surface together. And for them to be the same, that means we have to have theta I equals theta r. Another way to think of this is in terms of the conservation of momentum. So a reflection off of the surface by a photon basically means momentum is the collision is elastic, right? Since the collision is elastic, the x component of the velocity, right? The x component of the velocity of both of them has to be the same, and the y component simply reverses itself. Alright, those are equal. As I've drawn it off to the side here, as I've drawn it here, alright, you've got the incident photon coming in. Once it reflects, it has the same momentum. And it is, this component is the same, that component is simply the opposite, and by similar triangles we get that theta I equals theta r. This is called the law of reflection. Normally we don't notice this. Why? Because most surfaces aren't smooth like a mirror, are smooth like a pane of glass, or smooth like a metal sheet. Most surfaces are like this, right? They're all over the place, and so light gets scattered. In fact, the scattering of light like this is one of the important features of some of the materials that you use when making films and doing photography, that you spread light out in a incoherent way, in a diffuse way. The other thing about mirrors, right? If you are looking at a mirror, you look here, the reflection, those photons come in, reflect to get to your eye. Photons from down here come in, reflect. Well, I didn't draw that very well, now did I? reflect up, right, the result is the appearance of yourself, right, back behind the mirror. Now we're considering something different. Here we have, first let's introduce what's called the index of refraction. So in a media where the material does not allow the photons to move at the speed of light, but slower, we have what we call the index of refraction, which is the ratio between the actual speed of light and the speed of light of photons in this material. So this means that the index of refraction is always greater than 1, right? Since this velocity is always going to be slower than the actual velocity of light in vacuum. Alright. Because if you think about this wave coming in and propagating on through as it goes into another media, because the frequency is always the same, right? And we know the frequency is always the same by examining in detail what happens at the boundary, where electromagnetic field is going up and down and up and down and up and down. Well, it has to be going up and down and up and down on both sides of the boundary, right? So it's going up and down at the same frequency. So the frequency stays the same. And we write speed of light as lambda times frequency, or lambda, I wrote c, lambda at the speed of light times frequency, and we write the speed of light in the material as lambda v times frequency. What we get is the index of refraction is also the ratio of the wavelengths between light in the two media. What are some typical indices of refraction? Well, air is 1.0003. Now, vacuum is absolutely just 1, although space typically is not absolutely 1, simply because of cosmic dust, although it's very close to 1. Benzene 1.5, water 1.333, diamond 2.419, glass 1.6, right? And then there's an interesting one. It's an artificial material called aerogel. Aerogel is very close, right? Very close to being like air, right? Very close to being like air. And what I have picked here is a picture of some aerogel. And if it wasn't for the fact that it's slightly opaque, aerogel is very hard to actually see. This is kind of like asking you to see the air, a cube of air in the room. You can't, right? Well, aerogel is very close to being that. If it wasn't slightly opaque, you'd be very, very hard pressed to see it. And in fact, the one time I've seen some in person, it was a little block about like this one sitting on someone's desk. At first, I doubted I was seeing anything at all. So, aerogel is pretty cool stuff. It's also a fabulous insulator. It just happens to be expensive. Alright, now, law of refraction. We have two different arbitrary media, right? Then we know from what we had before that n1 lambda 1, right, the index of refraction times 1 equals n2 lambda 2. Why do we know this? Because we had that formula that says that this is equal to the wavelength at that frequency in vacuum. Well, this is also equal to the wavelength at that frequency in vacuum, so they have to be equal. If we look at the boundary, the space between the peaks at the transition point, right? So let's look here. We've got this triangle right here, right? There's that triangle. And then there's this triangle right here. In both cases, right? In both cases, oh, not there, down here, right? In both cases, that length from here to there and from here to there, right? That length is shared in common between the waves in the two media. If we call that length D, and this is a wavelength here, and this is a wavelength here, right? That length D is lambda 1 over sine theta 1. Remember, theta 1 is this angle, right? And that length, if you look at it from the other side, is lambda 2 over sine theta 2. Again, theta 2 is that angle, right? Theta 2 is that angle. So this yields sine theta 1 over sine theta 2 is lambda 1 over lambda 2, which is n2 over n1, right? We'll do a little bit more arithmetic, and we get to what's known as Snell's law, or the law of refraction, which is simply that, simply this: n1 sine theta 1 equals n2 sine theta 2. Right? What does that mean? n1 times the sine of this angle equals n2 times the sine of that angle. If we go off after this in terms of the momentum of the photon, right? What is the momentum of a photon? Well, momentum of a photon is h times the frequency over the c, or as we often write it, it's h nu over c. Nu is the frequency, but we use the Greek letter nu quite often in quantum mechanics, so you'll encounter this in P-Chem. H is Planck's constant, 6.626 times 10 to the minus 34 joules seconds, right? And nu is the Greek letter nu. So the momentum of a photon, hf over c, right? So if we look, remember that c equals lambda f. We can also write the momentum as p is h over lambda, or in the media where v equals, where the velocity is c over n, right? P is h over lambda n, which is nh over lambda, equals nhf over c. So P is the index of refraction times Planck's constant times the frequency divided by the speed of light. In region 1, that means P1, right, down here, P1 is N1 HF over C, and in region 2, it's N2 HF over C. At the boundary, no momentum is transferred to the media by the photon in the direction parallel to the surface. So if we look at the component, right, parallel to the surface, I'm going to call that the x direction. That means that N1 HF over C sine theta 1, which is the component parallel to the surface, equals N2 HF over C in sine theta 2. Again, the component parallel to the surface. Everything cancels except N1 theta 1 equals N2 sine theta 1 equals N2 sine theta 2, and we're back to Snell's law. A final bit about Snell's law, right? If we consider going from air into a medium where n is greater than 1, then we work through the math, and it turns out that theta 2 has to be less than theta 1. Then, as it emerges and comes out, it turns out that the angle coming out as you come out into a media where n is lower, right? As you go from a higher n to a lower n, the angle has to increase, the angle with respect to the normal. So we can generalize this. If n1 is less than n2, then theta 1 is going to be greater than theta 2. If n1 is greater than n2, right, then theta 1 is going to be less than theta 2, and that would be what's drawn here. One final bit about Snell's law before we move on, right? One final bit. If n1 is greater than n2, there's an angle where theta 2 hits 90 degrees. Remember, theta 2 is larger than theta 1, and so we can hit this angle where sine theta 1 equals n2 over n1 sine theta 2, and at the critical angle, right, it's critical angle, sine theta 2 is 1, right? So there's a critical angle sine theta c equal to n2 over n1. And at this point, sine theta 2 is 1 and theta 2 is 90 degrees. And we can go past that and say, well, we'll go on to the next step algebraically, right? Oh, pardon me. Go on to the next step algebraically. Say theta c is the inverse sine of n2 over n1 for n1 greater than theta 2. Once we go past that, we get total internal reflection, right? Total internal reflection. And total internal reflection is what makes a light pipe or fiber optic cable work. By putting the right materials together, you end up with total internal reflection. It's also what gives diamonds their sparkle, because light goes into the diamond and bounces around, and light gets collected, and it all tends to come out at certain points, causing the diamond to sparkle. Alright, that's enough about reflection and refraction and Snell's law and the critical angle. We'll pick up again with the next lecture.